Let A, B and C be three sets such that A union B equals to A union C and A intersection B equals to A intersection C. Now we've just replaced B with C here in this one, and we've replaced B with C here in this one. This means, this statement is saying that this means B is equal to C. So if this and this is true, then show that B is equal to C. Pause the video, give this a try. Okay, let's do this together. This is the strategy. We'll prove that all elements that belong to B, this set B, also belong to C. And if this works in reverse, then this means that B is in fact equal to C. If all elements in B are in C and all elements in C are in B, then this means both of these are equal. All right, let's begin. Let's assume that an element X belongs to B. So if X belongs to B, we can write this as X belongs to B. Now, if X belongs to B, X also belongs to A union B. In fact, it belongs to anything that has the union with B. X is in B, it belongs to A union B. And the question says A union B is the same as A union C, which means if X belongs to A union B, then it also belongs to A union C. These two are same, so we can replace this with this. So here's what we have. If X belongs to B, then X belongs to the union of A and C. If X is in the union of A and C, this means X is either in A or C or both. So let's take cases. Let's assume that X is in A. Now, if X is in B and X is in A, then X has to be in the intersection of both A and B. So X belongs to the intersection of A and B. X belongs to A intersection B. And from the question, we can say that A intersection B and A intersection C are same. This means that X belongs to A intersection C. We can replace this with this. These two are the same. Now let's see what we have. X belongs to A and X belongs to A intersection C. So X is inside A, but X is also inside A intersection C. So this means A has to be in C as well. So this means that X belongs to C. So we have proved that if X belongs to B and X belongs to A, then X belongs to C. Now let's go back. Let's assume here that X does not belong to A. If X does not belong to A, it's there in A union C, so it must be coming from C. Then this means X belongs to C. And if X belongs to C, then X belongs to C. So there's nothing to prove here. So we have proved that in both of these scenarios, X belongs to C, which means we have proved that if X belongs to B, then X belongs to C. So this works in this direction. And we might as well started with X belongs to C. We could have started with C and reached the same conclusion for B. This would have worked the same way. There's nothing special about B. So if all elements in B are in C and all elements in C are in B, then we can say that both B and C are the same sets. B is equal to C. Let's move on. Let's try some different types of proofs. Show that these statements are equivalent. We have these four statements and we have to show that all four of these mean the same thing. Pause the video, give this a try. Okay, let's do this together. Let's try a visual approach this time. Let's make these sets A and B. So this is A, this is B. The first one says A is the subset of B. So A is inside B, A is the subset of B. If we can prove that all the remaining three also give the same picture, or vice versa, if you can move from this image to each of these statements, we can say that all four of them are equivalent. So let's take them one by one. The second one says A minus B is phi. So if we subtract all the elements of B from all the elements of A, what do we get? Well, A has all the elements that B also has. So if we subtract the elements that B has, A is left with nothing. And that's exactly what's written here. A minus B is phi. The next one says A union B is B. So if you combine all the elements of A and all the elements of B, you get all the elements of B, because whatever is in A is also in B. A union B, from the image as well, you can see that it's equal to B. This last one says A intersection B is equal to A. If you take the intersection, if you take the area where they overlap, that's the area that A has. So A intersection B is in fact equal to A. So this same image is taking us to each of these four statements, which means each of these are equivalent. Let's try some more. Show that if A is a subset of B, then C minus B is the subset of C minus A. For that, we need another set, C. Let's try C minus B. Let's see where it is. So C minus B, subtracting all the elements that are in B, if you subtract them from C, we get this area, this orange area that's not in A or B. So this is what we have for C minus B. For C minus A, we subtract only this smaller part. So we have a bigger area from C where we have C minus A. So C minus A, as we can see from the image, does contain C minus B. Or you can say that C minus B can be made using the elements of C minus A. So this statement is true. Let's keep moving. Show that A is equal to A intersection B union A minus B. Let's find A intersection B. It's this area, union A minus B. The part which is in A but not in B. So this part. If we add these two, if we take the union, we get the entire A. That's exactly what this says. A is equal to this part which is A intersection B union this part which is A minus B. So A is equal to this union this. So this is true. Last one. Show that A union B minus A is equal to A union B. So if we take A and then we join it with B minus A is this part, B minus whatever's in A. So this orange circle plus this remaining green part, if you combine both of them, we get A union B. And that's exactly what this image is showing. Hence proved.